Okay, welcome to today's lecture. Today's lecture is about integrated rate laws. So under this topic, I'm going to teach you on how to come up with the integrated equations for the zero order, first order, and the second order. Not only that, I'm going to teach you on how to come up with the half-life equations for the zero order, first order, and the second order. So pay extra attention so that you can understand clearly. And first and foremost, don't forget to subscribe to this channel so that whatsoever I'm going to be posting, you'll be notified. So now let's start. So what do we understand by the integrated rate laws? So we need to understand this before we can do anything else. So the integrated rate laws of a chemical reaction shows how the concentrations of reactants change with time. So it just deals with the concentrations of reactants, how the reactant concentrations are changing with time, or it just relates time and concentration for a chemical reaction. So that's what you're supposed to know here. So as I was saying, the integrated rate laws, it is also useful to be able to express the reactant concentrations as a function of time. So here is just involving how this reactant concentration is changing with time, given the differential rate law for the reaction. So we will proceed by first looking at reactions involving a single reactant, like this one here. So this is a reaction involving a single reactant. So this reactant you are seeing here is decreasing with time in order to form this product, which is increasing with time. So if you watch the first video, I talked about the reaction rate. So the reaction rate of a chemical reaction. So reaction rate is just reaction rate is a change in the concentration of the reactants consumed or the products formed over a period of time. So it's involving change in the concentration of either the reactants or the products consumed or the products formed with time. So over change in time. But don't forget that this one A is decreasing with time in order to form this product. So decreasing, you're going to have negative there, like that. So this is how you come up with a reaction rate for this reaction you are seeing here. And then since you are saying we are using given the differential rate law for the reaction, differential now, that's calculus, that's mathematics now. So how can you differentiate this now? So rate is equal to negative. So this change will change in dA over dt, like that. So this is how the reaction rate will look like. And then in the second video that I posted, I talked about the rate law. Rate law, I said, this just shows how rate depends on the concentration of reactant. So rate is equal to, you need to write the constant K. How can you come up with a rate law for this reactant here? Since I said rate law deals shows how the rate depends with the concentration of the reactant. So the reactant is this one. So how can you come up with that? So you're going to come up with A, and then you need to write power n, like that. So this n, it will depend. I'm going to teach you about the zero order, the first order, and the second order. So I'm going to be substituting in this n. So just pay extra attention. So how can you come up with this? So it will be like that. So this is how you come up with the rate law. So this is a rate law. Wow, this is the reaction rate. So this is what we are going to be doing here. So O of the form, O of which have a rate law of the form. So have you seen this? What I'm from doing there? As you can see, this is the reaction rate, the one I demonstrated, I illustrated here. And then this you are seeing here, it's the rate law. They have just equated these two. So it's taking this form. So just pay extra attention. So this is what we'll be doing. So we will develop the integrated rate laws individually for the cases n1. When you say n is equal to 1, that's a first order. And then if n is equal to 2, that's a second order. And if n is equal to 0, that's zero order. So let's start with the first order. So what do you understand by the first order? So a first order reaction is a reaction whose rate depends on the concentration of a single reactant raised to the first power. So here our n is equal to 1. So it is raised to the the first power. So for a reaction of the first order of the type, this same type you're having, so the same thing will be happening here. Let's come up with the reaction rate for this. So the reaction rate, since A is decreasing with time, it will be negative. And then here we're going to differentiate this. So it will be dA over dt. So this is the reaction rate. And then let's come up with a rate law for this same reaction here you're seeing. So it's going to be K reaction rate. They should take the constant K there, and then the concentration you are having, and the N. Now this N, our N, we know our N is equal to 1 because this is the first order. So when you substitute in this N you are seeing here, when you substitute, what are we going to have? We're going to have something like 1 there. We're going to have 1 there on top there. We're going to have 1 because we have. So that's how these two, we're going to be comparing these two. So here the rate of this reaction is the rate. This is the rate now, the one I'm from showing you there. I'm sure this now you know where it's coming from, that one. And then also from the rate row expression we have, so this is the rate row now, this one I came up with. So it's power 1 now, 1, even if they haven't indicated, just the same. So now the next thing, because of the power of A is 1, the reaction we are considering is the what? First order, because the power is 1, the N is 1. So this one is the first what? Order. And then equating these two, so we're going to equate these two equations, this one and that one, so that we can come up with one. So it's going to look like this. So this one is the reaction rate, while this one is the rate row expression. So here we're going to do this, we're going to use calculus. We're going to integrate this. So after integrating this, we're going to come up with the integrated rate equation for the first order, which is applicable to the first what? Order. So by integration mathematics, we're going, so by using calculus, we will integrate and we obtain integrated rate what? Equation, which will take this form. So when you integrate, you're going to come up with this, and then this is taking the form of a straight line, which is mx plus b, where this y is this concentration you are seeing here, and then this m is the gradient. So here it's a negative slope, that's a gradient, and then this x is the time, and then this constant b is the initial what? Concentration, like that. So this as the form of the general equation of the straight line, this one. So this is what I'm from explaining there, and I'm sure it's clear now to you. And then thus for a first order reaction, a product of in A like that versus time must be a straight what? A straight line with a slope of negative k, like that. So that's the constant, and the intercept is what? The initial, like that. So here what they're saying is the graph for this should take this form there. So it should have in like that, and then it should be against time. So this is a concentration which is in A, and then this is time, and then since it's a negative, you are seeing this is a negative there, so it's a slope, it's dropping like this. So that's a negative, so it should take this form. So for the first order, just know the plot should be a slope of negative, so it should be dropping like that. And then we need to look at the half-life now. So half-life for the first order reaction. So the half-life of a reaction, so this means half-life is the time required for the concentration of a reactant to drop to 1/2 of its initial concentration. So take note on that, initial what? Concentration. So half-life of a first order is the time taken for the initial concentration to drop to 1/2 to, or to drop to half, to drop to 1/2 or half of its what? Original amount. So that's what you need to know there. So for the half-life, we are considering the initial concentration, not the final concentration. So this is what I'm talking. So first, by definition of half-life, when t is equal to, so this is half-life now, then it's going to take this form. Why is it taking this form? We need the half-life of the initial concentration, not the final concentration, because we are saying half-life is the time required for the concentration of the reactant to drop to 1/2 of its initial concentration. So this initial, we are multiplying it with 1/2, because we want to find the half of this initial concentration. So after that, thus half-life for the first order reaction is going to take this form. So now you can ask your question, where is this thing coming from? So let me show you where this thing is coming from. Let me try to prove. So this is the formula for the half-life. So t, this one, t 1/2, that means half-life is equal to this. So where is this thing coming from? So let me try to illustrate or show you. So if you can remember the integrated rate equation, it was like this. In, we had the final concentration like that, and then we had negative kt like that, plus in, and then we had the initial there like that. And then here our aim is to make this t the substitute formula, because this is our half-life like that. So what do we do first? So we're not considering this final concentration, we're considering the initial concentration, because we said the half-life is the time required for the concentration of a reactant to drop 1/2 of its initial. So I'm going to write the initial here, the initial. So initial like that. Let me just lap, and then let me lap and write it like this. So here we're going to have something like this. Yes, so here we're going to have in like that, and then I'm going to say 1/2, and then I'm multiplying it with the initial concentration like that. So and then it's going to be negative k t 1/2 like that, plus we're going to have in, then the initial like that. This one I'm multiplying half with this because I'm trying to come up with the half-life of the initial concentration. So when I multiply this by that, so in of 1/2 and this concentration, it can be written like this. In, I'm going to have for 1/2 separate, plus in of this concentration, initial concentration you're seeing there like that, and then is equal to, you just write this thing here, just copy it like that. Yes, like that. And then here your aim is to remain with this, but have you seen these two are common, this side and this side, so you cancel, and then you're going to have in 1/2 like that is equal to negative k t 1/2 like that. Now here what do? You want to remain with half this t here. So what do? You divide both sides by negative k. Then when you cancel, we cancel this, you're going to have something like half is equal to, this can be written like negative, this negative, it's the one you're seeing here, and then I'm going to have in 1/2 there over k. And then here we're going to have something like this negative you're seeing here, and then when you do in of 1/2 on your calculator, you're going to get negative 0.693 like that over k like that. And then this negative times negative will cancel, therefore you're going to have your half-life to be half-life is going to be 0.693 over k like that. So this is how the formula is coming from. So this is the formula now you're seeing here. So I'm sure now here it's clear. So that's the formula now. So I'm sure now you know where this thing is coming from. So as simple as that, then we can proceed to the other one, to the second order. So on the first order, I've showed you now to come up with the integrated rate equation, and then I've showed you how to come up with the half-life. I've showed you where it's coming from. Hope it's clear. And then you need to know the units for the rate constant. So for the units the units of the rate constant k for the first order reaction is this. So for this, for you to remember, you need to know that this m for your concentration is 1 minus n, and then you're going to have t like that. So here what you're supposed to do is your n is 1. So what do? m1 minus 1, and then you're going to have t. This t is just like that, it's not having n or what, so no need to, you don't have what to substitute there. So here 1 minus 1 is going to give you 0 like that, and then here t like that. But this t it's in seconds, so time can be in days, in hours, in minutes, but it's in seconds, so it's going to take this form. This is same as 1, so we're not having any constraint. So this one becomes the units for the rate constant for the first order. So for the second order, if you want to come up with the units for the rate constant, use this. So for the second order, we're going to use what? 2 instead of what? 1. Hope it's clear there. Now let's do for the second order now, so that you can understand. So what do you understand by the second order? So a second order reaction is a reaction whose rate depends on the reactant concentration raised to power 2, or on the concentration of two different reactants each raised to power 1. So it can be raised to power 2, or on the concentration of each of the two different reactants each raised to power 1, of which when you add them you're going to get 2 again. So that's for the second order. So a simple second order reaction involves only one kind of reactant, same with the first one, so it's the same thing. So here, if you can remember what I said, the reaction rate is going to take this form. I'm sure I've showed you where this thing is coming from, so by this time you understand. And then what will change here is just the order, the retro will change to be different with the first one, because N now is 2. So retro is going to, for this reaction, is going to take K, then the concentration, and then N. But your N here now is 2. Your N is 2. So it's going to be let is equal to K, and then you're going to have power 2 like that, because it's the second order. So this is how you can know the second order, because of that power 2. So the retro expression for the second order reaction is given by this. So this is what I'm from explaining there, and I'm sure you understand. Now we're going to equate this reaction rate and the retro expression. So equating these two, we're going to have something like this. So this is the reaction rate, while this is the retro, and then we're going to use the calculus. We're going to integrate this so that we can come up with the integrated rate equation for the second order, as we did on the first one. So after doing that, so using calculus, we integrate and obtain the integrated rate equation applicable to second order reaction, which will look like this. So this is taking the form of a straight line. So this is done mathematically, and then the same thing, y mx plus b, like that. So this is for the y, this shows the y, and then this is the slope, which is k. Now this time we're having a positive, so this time it's going up, not down. And then this x same as the time we're having there, and then this is the constant b, which is the initial concentration, like that. So this equation has the form of the straight line equation, so this is what I'm from explaining there. And then now let's talk about the half-life now. So the half-life definition is just the same. It's just the time taken for the initial concentration to drop 1/2 of its original amount. So half-life for the second order reaction. So for a second order reaction, half-life, we have this. So this is half-life 1/2, and it's taking this form. So here we're just interested in the initial concentration, so we're going to multiply 1/2 or half of this same initial concentration. We're going to multiply it with 1/2. So after doing that, we're going to come up with this. So where is this thing coming from? We need to know where this thing is coming from. So from the integrated rate equation, you saw there, it was like this, where this was the final concentration, and then here it's positive K, like that, plus 1/, the initial, like that. Our aim is to make T the subject of the formula. So what are we going to do? Here we're not going to consider the final, but the initial. We want to find the half of the initial concentration. So I'm going to say over, like that, 0 is equal to K, which is the rate constant, the half-life, plus 1/, the initial concentration, like that. And then I'm going to multiply this by 1/2, because you want, have you seen this part? Yes, 1/2 of that, because it's I want to find the half-life of the initial concentration, not the final concentration. So when you multiply this by that, before you do that, 1 divided by 1/2, we are going to get 2 over the initial concentration, like that, which is equal to K T 1/2 plus 1/, the initial concentration, like that. Your aim is to remain with this T. What do? These two are like 10, so this can go that side. When it goes that side, we're going to have something like 2, the initial, like that, minus 1/, like that, is equal to K T 1/2. When you subtract this, so since the denominators are the same, so you can subtract there. So 1 or 2 minus 1, you're going to have 1/, the initial concentration, like that, is equal to K 1 over 2 like that. Then here, what do? You want to remain with the half-life. It's 1 so we're going to divide k both sides. So here you're going to have 1 over 2 is equal to, we are dividing with k now, so the initial, so divided by k. So after working out that, you have something like okay, let me just finish it so that you can understand whatever is being done here. So divided by k, so here same as 7 1, and then when it's like that, what do? Same as 1 over the initial times 1. This one goes up when you introduce the multiplication sign. Then what will happen? You're going to multiply these two. So we multiply 1 times 1, you're going to have 1, the one you're seeing there on top, and then k times this, you're going to have something like this. So this is where this thing was coming from. I'm sure it's clear. Now we can proceed to the zero order so that you can understand clearly. So this thing, you just have to know it by heart. They won't ask you to show where these equations were coming from. I was just trying to show you so that you can know where this thing is coming from, and you can know how to use it. In case you forget, you know where to start from. So this is how you come up with this. So just take interest in these things, then you'll make it. You get your A+ in chemistry, which is very possible and simple. Okay, now let's proceed. Okay, so now you know where this thing is coming from. So first, the half-life of the second order reaction depends on the initial concentration of the reactant and the rate constant. So as you have seen here, so the half-life of the second order reaction depends on the rate constant and the initial concentration. And then the units of the rate constant for the second order reaction are these. So these are the units. As I said, if you can remember on the first order what I did, 1 minus n. Then here I had to write t like that. So here now, since it's a second order, n is equal to 2. So m like that, 1 minus 2. We're going to have something like this. So here, the fine, we're going to get -1. And then this time, it can be in seconds, it can be in days, it can be in hours. So this time, seconds like that. So this is how you come up with the seconds. So you just have to use this expression, simple expression here, to be helping you with units, because the units for the half-life, for the rate constant, for the first order, second order, and zero order are different, but this thing is going to help you, this expression. So take note of that. Now let's look at the zero order reaction. So for a zero order reaction, we have in this reactant, single reactant, decreasing with time in order to form the product. So the integrated rate equation can be combined. So the rate row expression for this, how can you come up with a rate row expression? So for the rate row, it's going to be different, the first one and the second one. So rate is equal to k, and then we're having the concentration n. Now here, our n, since it's a zero, we're having 0. So rate will take this form. So here we're going to have 0. But according to the rules of indices, 0, any number or any letter to the power 0 is same as 1. So we're going to have just k like that. Because here we're going to have 1 times k, we're just going to get like that. So it's going to take this form here. And then also the reaction rate is just the same. This one I did on the first part, and I'm sure you understand. So this is just changing the concentration of A, and then changing what? Time. So equating these two, we're going to it's going to take this form, where this is the reaction rate, and then where this is the order of the zero the rate row for the zero order. And then after doing the integration of these two, after integrating this, we're going to integrate this. After doing mathematics, we're going to we integrate and obtain the zero order integrated rate row. So after doing the mathematics calculus, we're going to come up with this integrated rate equation for the zero order, where this is equation is taking the form of the straight line like that, and then where this y is this, y is this, and then this m is the gradient, which is the slope. This time you're having a negative, and then this x is corresponding to time there t, and then this is the initial concentration. So this is what I'm from doing there, and then the product of A concentration, this one concentration versus time, gives a straight line for a zero order reaction. So it gives a straight line. So the slope and the intercept of the line are negative k and the initial concentration respectively. So if I told you are supposed to plot this one, it's a it's dropping like that. It's a negative against time, so this concentration against time, so it's, since it's a negative there, the slope is negative. But for the what, for the second order, I didn't show you. Here it's positive, here it's positive. I didn't show you how the slope can be. Here you're having a positive, so for this one it can be like this. So this one is time, and then you're going to have 1 over like that, and then this one is going up because this k is what, positive. So you just have to know in terms even of the graphs. So since now that I've showed you, we can move on now. Okay, where are we now? Okay, so I'm from showing you this. Okay, so this is what I'm from doing. Now let's go to the half-life for the zero order what, reaction. So half-life, the definition is just the same. It's just the time taken for the initial concentration to drop 1/2. So here, like in the case of the first and the second order reactions above, we substitute this, which is the half-life, and you're going to take this form now. So we're not considering the final concentration, but the initial concentration. We're multiplying half with to the initial concentration because we want to find the half-life of the initial concentration in the zero order integrated what, equation. So we get this. So where is this thing coming from? We need to come up with the equation from doing there. So here for the zero order, we know that the integrated rate equation is taking this form, the one I am from showing there, like this, plus you're having like that. So your aim is to make this as your subject of formula, because this is the half-life now. So what do you do? What do you do? You are having just simple algebra, you're having this and this, so this can cross go in that side. Or before we do that, let's need to multiply the, we're not considering this, we can do this first, is equal to negative k 1 over 2 plus the initial concentration, like that. So here I'm going to multiply this initial by 1 over 2, like that. Once you multiply it with 1 over 2, we're trying to find the initial, this part of, we have seen it, so the half of this, the half-life of this initial concentration. So here now we're having algebra, so this can cross go that side. When cross going to be negative, or another way, just have to do negative of this so that we can get rid of this. Even here negative of that. So what are we going to have now? So here, after working out this, subtracting that, you're going to have negative 1 over 2 of this concentration initial, which is going to give you this. We have subtracted, right? So we are cancelling that, negative k 1 over 2, like that. And then your aim is to remain with this this. So what are you going to do? Before you do that, you can multiply 1 times this. You're going to have negative of the concentration over 2, and then you're going to have negative k, like that. Then here, what are you going to have? You are going to have something like you can even first divide if you want here, negative k, and then here what do? You cancel, you cancel. So your half-life will take this form. We're going to have negative of the initial what, concentration over 2 divided by negative k. This can go so 1 over 1 because you balance it, and then you're going to have 1 over 2. Then here, what do? Negative of the initial concentration over 2. When you do the multiplication, this will go up, this will come down. So you're going to have 1 there, down there, and then when you and then this is negative k, like that. When you multiply this by that, we're going to have something like negative of the concentration of the initial, and then this time is going to have negative 2k. You cancel this, your half-life will be like this, so it will take this form now. So hope you will get where this thing is coming from, and we are done. I've showed you for the half-life and the integrated rate equation for this. So now let's do the other part now. the last part so that we solve some questions, and let me show you last the units for the rate constant for the zero what order so that you can understand clearly. Hope it's clear, and you just have to put this in a practice. Don't just watch the videos, practice, and you become good at these things. So these things are very sweet and very simple, and I know for as long as you're watching this, you're going to get your A plus. Never doubt yourself. You're slowly getting there. Just put this thing in practice. Nothing beats interest. So thus the half-life of a zero order reaction depends on the initial concentration of the reactant and the rate constant. So as we've seen here, it depends on the initial concentration of the reactants and the rate what constant. So the units of the zero order is taking this form. So why is that? Why is it in that form? We know that 1 is equal to n t like that, and then our n is equal to 0. So m 1 minus 0 like that, then t like that. So this 1 minus 0 is just same as m, and then this times can be minutes, days, so this time seconds. So this is the how you come up with this. So master this, please. You need to know how to come up with the units of the rate constant because they are different. Now let's do this last question, or maybe I'll do this one and the other one. Yeah, so let's do this question now. So what's the question saying? A certain first order reaction has the half-life of 20 minutes. Calculate the rate constant for this reaction. So how can you calculate the rate constant for this reaction? So you know that this one is the first order. So let's come up with the formulas for the first order. The first formula I showed you is the integrated rate equation for the first order, which is taking this form. The final is equal to negative kt plus in of the what initial concentration, and then I showed you the half-life, which is like that, 0.963 over k. So here now we can use this second one because it's asking us to find the rate constant k. So on your data you are having k is the one you asked to find, and then you have the time, which is 20 minutes. Yeah, and then so let's use that formula. So here half-life is equal to 0.963 over k. So here now our aim is to make this k the substitute form, since they want the rate constant. So we're going to have k times the half-life 1 over 2 is equal to 0.963 like that. Your aim is to remain with k, so you divide both sides by the half-life, even this side over the half-life. So when you cancel like that, your k is equal to, you substitute now. So here you're going to have 0. Okay, let me write it 0.963 like that over the time, which is the 20 minutes. So what are you going to get? You're going to have something like when you divide these two, we are having 0.03465 minutes. So this first order is going to be like that. Then you're done for the first part. You said for the unit, for the units of the rate constant, I'm sure you know where this thing is coming from. We said it's supposed to take this form. So here now, this is the first order. So your n is 1, so you subtract it 0, so 0 will disappear, and then your time is in minutes, so it will take this form you're seeing here. Hope you get where this thing is coming from. And then let me show you now how to solve for the second question now. So this is how you do it, and then we're going to keep this rate constant, our answer, because we'll use it on B. Yeah, on B we use the same one here. So okay, hope it's clear. Okay, so B, what is B saying? B is saying how much time is required for this reaction to be 75 what percent what complete. So we're having our rate, which is 0.03465 minutes, like that. So this is our rate. So let me lab here. Okay, so how much time is required for this reaction to be 75% what complete? So here on B, we're going to use this in of final is equal to negative k t plus in of the initial concentration, but this can take this form. In, we're going to have the initial concentration on top over the final, or the T1, like that, then is equal to, this time we're going to write k t like that. So this can be written like that. If you want, you can take it like that, it's okay. And then here now you need to come up with your initial and your final, and I'm going to show how to do that. The rate we have already, they want now the time. So here they want this time, it's the one you're looking for. Now here just by the question, the way the question is saying, it's saying at time t, time is equal to 0, you're having this is 75%. So at time t we're having 100 what percent. So this 100% you are seeing there, it's the initial what concentration. That's the initial what concentration, and then it wants what 75% compression. 75%. So for it to reach 75% compression, we're having 25% remaining. So 25% concentration what remaining. So here we're going to have the final concentration one, which is going to be 25 what percent. And then here what do? You take this one in a ratio, it will be what? So 25 divided by 100, because it's 6%, you're going to have 0.25. And then the ratio of this initial, you're going to have it's going to give you 1, just 100 divided by 100, so it's going to give you that. So for the initial concentration we have, it's 1, and then for the final, it's this one. So we can use this now. So in, what's your initial? It's 1 over 0.25, like that, is equal to, what's your k? Your k you have, it's that one there, which is 0.03465 minutes, like that. And then you want t. So when you do in of 1 over 2 on your calculator, you're going to get something like 1.38629 is equal to, you write this 0.03465 minutes, like that. Then you want to remain with what? The time. So you're going to divide both sides by 0.03656 what 5, like that, minutes. Even this side 0. Oh wait, okay, so here there's a mistake. Okay, sorry for that. So after dividing this same concentration, this side and this side, there are the challenge there, 0.03465 minutes, like that. So this divided by that, your time will be 40 minutes. Your time will be 40 minutes, like that. So sorry, here I'm at the challenge, so I'm sure you know what's happening here. So that's